Hello students, we are almost at the end of module 2. This would be your penultimate lecture, and what we have seen so far is how the instruction gets executed, and then we moved on how we can improve the performance by improving basically by improving the rate of execution with an idea called pipelining, right? And then we started looking at what are all the possible difficulties we would get to get the pipelining implemented, and accordingly we addressed many assumptions that we made. And the last few classes we looked at the structural hazards, data hazards, and control hazards, how we address them at the hardware, and can we do something at the software. In this lecture we are going to look at some special scenarios that the pipelining needs to handle, right? Now if we think about what are the special conditions to handle, again these conditions are those events that will again disrupt the pipeline flow, right? Now let's see what they are. Typically, what disrupt the normal flow of instructions are called exceptions or interrupts, right? They are any unscheduled event that disrupt the program execution, and sometimes these events can also be useful to handle some undefined conditions. I'm going to touch upon this as we go, right? And typically, these exceptions are something that come from outside the processor, and that is a more generic definition. But if you want to restrict to this particular user program, these are some exceptions that are out of the user program. Okay, and a quick note on the terminology: we would come across exception or fault or interrupt, right? All of them mean the same thing. There are some special condition that the pipeline needs to be prepared for, and different exceptions, different events, right? Like these need some different support from the hardware. And if we want to see what all exceptions typically are there, right? The very first one is input output device request. The second one is invoking the operating system, and this can be done by the user program itself, right? The third exception is tracing the instruction execution, right? This you have already seen in your practice labs. You use the functionality which is step, right? You want to trace how the instructions are getting executed. That is an example of exception. The fourth one is breakpoint. Again, it is programmer requested, and if you are familiar with GDB based debugging, right? So you use breakpoints a lot, right? And even instruction tracing can also be done by stepwise execution, right? And both of these are there in Venus. The fifth event can be an integer overflow, and sixth is some anomaly with the floating point arithmetic. The seventh event is called page fault, wherein what data we need, either the instruction or the data, right? It's not currently available in the main memory, right? But we know what to do. What we would do is we get the same data from our hard disk and place it in the memory and get start work again. But the event of identifying that the data we want is not there in the memory is called page fault, and this needs some support from the operating system to handle the transfer of data from the secondary or your hard disk to the RAM. Eighth condition is misaligned memory accesses, right? If the memory is an aligned, expects the access to be aligned and some address is given that is not aligning, then it can potentially throw a exception. The ninth event is memory protection violation. It means that we are trying to access some data that does not belong to the user program, or somebody else is trying to access the data uh, that doesn't belong to it, right? The 10th example or event is using an undefined or unimplemented instruction. 11th one is hardware malfunction, and 12th one is the typical power failure. All these are classified as exceptions. I would give I have already given a couple of hints on how many of these are already in Venus. I'll leave it to you on to think more about how many overall are there in Venus. Okay, just give it a thought. So let's look at the events that can potentially occur in our 5-stage pipeline. Right, during the fetch stage, we can encounter a page fault, or it can be a misaligned memory access, or it can be a memory protection violation error. Basically, we are trying to access the instruction memory, right? And so these three are the potential scenarios. In the decode stage, we will typically encounter the exception of an undefined or unsupported opcode. In the execute stage, we can see the arithmetic exception or the floating point exceptions. Again, in the memory access stage, we are trying to access the data memory, and the exceptions we can see are similar to the fetch stage, right? The page fault, misaligned access, or memory protection violation. And in the fifth stage, which is the write back, we are just trying to access the registers. Nothing specific would come. Overall, these exceptions are categorized, and this categorization is primarily done to understand what support each of them need, right? The very first category is whether an exception would uh, is a synchronous exception or asynchronous exception. Synchronous means that this exception would occur at the same time every time when we are executing the program with the same data and memory allocation. Asynchronous meaning that this is typically caused by external devices. The second categorization is whether the exception was requested by the user or it's not. Otherwise, it's also called coerced. If the user has requested for it, then it's called user requested. Typically, the coerced exception would be caused by some hardware event which is not under the control of the user program that is currently under execution. Okay, coerced exceptions are typically more harder to identify and implement. The third category is user maskable and user non-maskable exceptions. If the user program can enable disable any of the exception, then it's called a user maskable exception. If the user program does not or cannot do that, then it's called non-maskable. So as we look at some of the examples, you would get more clarity. The fourth categorization is within and between instructions. An exception which will occur uh, within an instruction, meaning that it will prevent the execution of the current instruction, right? It's called a within instruction. Otherwise, it's called between instructions. Um, Typically, within instructions are synchronous, and within exceptions are synchronous, and between instructions kind of exceptions are asynchronous, and within exceptions are harder to implement. The fifth categorization is whether the exception is of type resume or terminate. What it means is once the hardware sees an exception, whether it will terminate the program or it will give us an option to resolve it and continue the program execution, right? The terminating exception that you might be very familiar with is the segmentation fault, right? Typically that would happen if you're trying to access a memory location that's not allotted to the program. That is a terminating because the program does not progress further. But on the other hand, if you put a breakpoint and once you clear that, the program can continue to execute further. So they are called resuming type of exceptions. Now let's see all the exceptions that we have seen prior and try to classify them into each of the categories. Right? The input output device request is typically an asynchronous exception, and it is coerced, not user controlled, and it is not maskable by the user. It means that it's non-maskable, and it typically is categorized as between instructions because it will not stop any instruction from completing its execution. And typically these requests are resuming type. If the user program is requesting some facility or some utility from the OS, it would be a synchronous exception. Again, it is requested by the user, it is not maskable, and it is something that comes between the instructions, and it after the OS service is utilized, we come back to the user program and complete its execution. The third one is tracing. Again, this is more or less straightforward. It is synchronous, it is user requested, it is maskable because we can enable or disable tracing, right? And it belongs to between instruction type of exception because if you put a step, it doesn't necessarily stop the instruction to execute, right? Rather, it's giving us a handle on what is the status after some instruction got executed. And it is a resuming type of exception. The fourth one is breakpoint, and you would have already guessed it is similar to tracing. It is synchronous, user requested, maskable, between, and resuming type. Integer overflow is synchronous because if the hardware, let's say the addition of two numbers is giving as an overflow, every time you run the program with the same input, it will still give the it will still throw an overflow, right? So it's a synchronous, it's a coerced one. We don't typically expect that overflow should happen, right? And it is maskable, meaning that if the user says, okay, you can overlook this overflow, you can continue with the execution, and it will happen within the instruction execution, meaning that when some instruction is getting executed, right? It means that it is in execute stage, and in that particular stage we see an overflow. It will never progress to the memory and write back stages. It will stop there. So this is the within instruction type of exception, right? And once it is resolved, we can resume with the program execution also. Floating point overflow again belongs to the same category. It is synchronous, coerced, maskable, within instruction type, and resuming type. Page fault is synchronous, coerced, and we cannot mask it because we cannot overlook saying that okay, by mistake I have generated the address, please overlook and continue. That doesn't happen, right? And it is within type of instruction, exception, meaning that let's say you're trying to access the data memory in the memory access stage, and that threw a page fault that resulted in a page fault. What would we do? We cannot progress to the write back stage anyways. And it is resuming type in the sense that when the OS identifies that the page fault has occurred, it will do something and makes the data available to the program. From there on, the program's execution can continue further. Memory misalignment is synchronous, coerced, maskable, within, and resuming type. Memory protection, on the other hand, is synchronous, coerced, and non-maskable because it will result in a serious condition that the OS intervention is typically needed. If some malicious software is trying to access your secure data, for example, the OS would typically be given a heads up, right? Or some other monitoring software will be given a heads up. So it cannot be masked. If it is masked, then the malicious software will always disable it, right? An unidentified instruction is synchronous, coerced, and again it is not maskable. Let's say our hardware does not have ADDI type of instruction. Now, if the compiler has generated an ADDI, what will we do, right? So it will, in that case, it will throw up an warning saying that ADDI is an unidentified instruction. It will stop the execution. So that's why it's called, it belongs to terminating type. Hardware malfunction, it is asynchronous. We don't know when it happens typically. It is coerced, it is not maskable, it is within type instruction, and it will terminate. Power failure, this is the most common one we would see again, right? It's an asynchronous, coerced, non-maskable, within, and terminating type. Now, how do we handle any of these exceptions? Let's see the tablet of how we'll do. This is similar to the way we would handle the procedures or functions at the assembly, right? What we need to imagine is there is some set of instructions that will be handling the exception that has arisen. Now, what we need to do, or what we are expected to do, is when some particular exception has shot up, its subroutine is called. And once the subroutine is executed, the exception is resolved, we expect the control to come back to the user program. So this subroutine is called interrupt service routine, ISR. So among all the exceptions that we have looked at, many of them are happening within instructions, and many of them are resuming type. Now, to handle such within instruction and resuming type of exceptions, the pipeline, whenever the exception shoots up, needs to be shut down safely. And as you might have already guessed, there might be many instructions currently under execution. So we need to know which instruction is in which stage, so on and so forth. That's called the state, right? We need to preserve the state, and we need to identify the instruction that has resulted in this exception, so that once the exception is resolved, we'll start from that specific instruction, right? Because of that, we need to have the PC. PC is the address of the faulting instruction here, right? And just like typically we use JLR, right? When we want to come back to the caller, in the same way, you can expect that there is a JLR at the end of the interrupt service routine, and in that will be pointing to the instruction that has originally resulted in a fault. Let's continue further. Now, whenever an exception occurs, the pipeline control, right, takes some steps. The very first thing it does is it introduces what's called as a trap instruction. Basically, trap is, you can imagine, are a set of controls that will help us to stall the pipeline at some particular point. So you can imagine it similar to stalling itself, right? Now, until this particular trap instruction is disabled by the pipeline control, right, none of the operations like writing to the memory will happen, either by the faulting instruction or the instructions that are following it in the pipeline. All right, basically we have stalled the pipeline, so nothing makes a progress. Now, after that, the pipeline control will signal the OS saying that its help is needed, right? The OS will come into the picture. It will save the PC of the faulting instruction. And in the previous class, we studied about delayed branching, meaning that we need to store some extra information, means additional PCs that are equal to the length of the branch delay plus one uh, if it is delayed branching, right? So all this information needs to be saved somewhere by the OS, and then the OS will execute the ISR, and once that is done, it will use the PC to come back to the user program, the original program, you can say. So let's look at a quick example here. Let's consider a sequence of instructions. Let's say this is our user program, right? The 40, 44, 48, 4C, 50, 54, etc. are the hexadecimal addresses, the PC of the instructions sub, add, or add, sub, and LD. Okay. Now let's say there was some particular exception that can happen, hardware malfunction, and its interrupt service routine starts at an address 1C09 followed by 4 zeros, and there are some set of instructions that it has. So whenever we see this exception, we need to execute this interrupt service routine so that the exception is resolved. Now let's say that this exception has occurred when the add instruction it was in execute stage, right? Now let's go step by step, right? We have the user program, we have the ISR, and here is the time flow. So we have the cycle number and fetch, decode, execute, memory access, and write back. So in cycle number 1, we will fetch sub. In cycle number 2, we will fetch and sub would move to decode. In cycle 3, we would fetch or, and would move to decode. Sub would move to execute. In the fourth cycle, we will fetch add, or will be decoded, and will be under in execution stage, and sub will be in the memory access stage. And in the fifth cycle, we fetch the next sub instruction, add will be in the decode stage, or will be in the execute stage, and will be in the memory access, and the first sub instruction that has entered the pipeline would reach its write back stage. In the sixth cycle, we would fetch the load instruction, sub would be in decode stage, and add is in its execute stage, or is in memory access stage, and is in the write back stage. At this point, our assumption was when add is in execute stage, we would see an exception, right? At that time, the hardware, specifically because we are dealing with RISC-V ISA, it has a specialized register which is called SCOS, right? It will indicate which type of exception it is. Let's say it is an overflow, or let's say the adder stopped working, because we are dealing with hardware malfunction, right? So let's say the adder did not work. That will be the reason that is stored in SCOS. This reason will be noted by the operating system, and it will store the PC that has resulted in this fault or exception in another specialized register which is called SPEC. So here the add instruction has resulted in a fault, so its PC, which is 4C, will be written into SPEC. After this, the operating system will start loading the instructions or executing the instructions from the ISR, right? So it would bring in the, ideally in the 7th cycle, if the fault did not occur, that's the way we would have progressed, but we have not made the progress. You can imagine the trap instruction is there, right? But the OR will still progress, and eventually in the next cycle it will complete, right? But in 7th cycle, the interrupt service routines instructions get fetched. So the first SD instruction is getting fetched in cycle 7. The second instruction would get fetched in the 8th cycle, and the first SD is in the decode stage. So on and so forth. We will continue executing the ISR, and let's say after a few instructions the exception has been handled, and uh, the operating system decided that it needs to go back to the user program. How does it do it? It will use the value in SPEC, which is 4C here. This is the PC. It will start fetching the instructions from there. So which is add in our case. So in cycle number 50, it will start fetching add, and 51, the next sub instruction gets fetched, so on and so forth. So this is how the hardware malfunction exception was handled by both the hardware and software. And in a typical cycle, there can be multiple exceptions that can happen. Let's say there was hardware malfunction, and at the same time there was some request by IO device, or maybe there is a power failure. So the operating system need to prioritize these exceptions and handle them one by one, but it surely needs to handle all of them. Right now, how does the operating system identify which exception we are seeing currently? There are two wide approaches that are primarily used. Right, the first one is the instruction set architecture itself can provide some additional information in a specialized register. Right, the operating system will look at this register, and then it will identify which exception has occurred. The second method is that the ISR, interrupt service routine of the exception itself, will give some information on what exception it is. Right, this approach is called vectored interrupts. RISC-V follows the first method, wherein some additional register is given, which will be checked by the OS. That additional register, like I explained in the previous slide, is called SCOS, Supervisor Exception Cause Register. This will hold the information on the exception. And the place where the PC of the faulting instruction, or the instruction where we need to restart the execution, is stored is called I think in the previous slide I spelled it wrongly. It is SEPC, Supervisor Exception Program Counter. It's a 64-bit register to hold the program address of the instruction from where we would expect to restart our execution. And overall, we have discussed what is the role of the hardware and what is the role of software, here specifically the operating system, on handling the exceptions. Right, the hardware will trigger the event, and the operating system will respond on that trigger, address the exception, and gives back the handle to the hardware to go ahead and execute the user program. By the way, even the operating system is running on the hardware. Okay. Now, if we are specifically able to identify which instruction has caused the fault, right, or the exception, it's called precise exceptions. Right, and what it means is the pipeline can be stopped at that point, and all the instructions that have entered the pipeline before this fault can still continue their execution, but all the instructions which have entered the pipeline after this faulting instruction will get stalled. Right, that's what we saw earlier in the earlier example. Right, so what happens if precise exceptions are supported is, the once the ISR is executed, we'll start from the faulting instruction and continue our execution. So supporting precise exceptions is one of the basic requirements of the hardware. RISC-V is precise. If we are not able to specifically identify the instruction that is causing the fault, it is called imprecise exception. In such cases, once the ISR is executed, it is duty of the operating system to pick the instruction in that any of the instructions in that state that was saved, and start executing the program again. Right. So in the previous example, if it was imprecise, for example, it can start the execution from PC 58 hex itself. right? There is you can sense that it is not always correct, but it is easier to implement when compared to precise exceptions, because precise exceptions need some extra information to be saved and retrieved. So the basic difference between precise and imprecise exception is, are we able to associate an exception with its um, instruction? If we are, then it's called precise. If we cannot, it's called imprecise. Right. With that, I will pause this lecture. And all the material that I have discussed today is available in Appendix A.4. Uh, Not complete A.4, read till A4, 45 page only in Computer Architecture, a Quantitative Approach book. And specifically to understand how RISC-V handles exceptions, the example that I have walked through, you can find it in section 4.9 of the Computer Architecture and Design book by the same authors, Patterson and Hennessy. Okay, go through the material. If you have any questions, you can ask me either over Piazza, or we can discuss in the live session. With that, I will pause this lecture. Thank you.